Okay, second question. Sketch y equals to negative x cubed plus 7x squared minus 15x. And our aim is to not only draw the graph, but also figure out the extrema and also the inflection point. We're going to get exactly one. Let's try this. Okay, first, what's the y-intercept? Y-intercept is you set x equal to 0, that means y is equal to just, if you plug in 0, 0, 0, it says 0. So 0 comma 0 is the y-intercept. Now to get the x-intercept, you would do negative x cubed plus 7x squared minus 15x equal to 0. So the x-intercept is the same as the 0 of the polynomial. I can factor this by negative x, and that gives you x squared minus 7x plus 15 equal to 0. This one just creates x equal to 0, which is just the origin, which we already have here. This one, you can quickly try a few numbers and determine that you can't factor this. So in order to get the answer for this, you end up having to do quadratic formula. With the quadratic formula, negative of negative 7 plus minus square root of 7 squared is 49, minus 4 times 1 times 15, minus 4ac. A is 1, c is 15, over 2 times 1. Now, 4 times 15 is 60, right? 49 minus 60 is? Well, we look here, it's a negative value. What does that mean? It means that it doesn't have any real solution. It will give you imaginary solution, but imaginary solution doesn't have anything to do with the graph. It means that we only have one single x-intercept, which is the origin. Okay? So that's all this work just told us that the only place that the graph will pass the x-axis or y-axis is at the origin. Other places it's not going to pass through the x or y axis. Okay, now let's try to figure out y prime. If you differentiate, 3 comes down, subtract 1 from 3, you get 2. 2 comes down, 2 times 7 is 14. And you get negative 15x, negative 15 because x differentiates to 1. This one can be factored using some technique called factor by grouping. If you know that, that's wonderful. You may use it. If you don't, then the only other method you can use is the quadratic formula. Both will give you the same answer, except that the quadratic formula will be a little painful. Because you have to square 14. 14 squared is 196 minus 4 times. So I guess it's not too bad. Yeah, but anyways, you have to factor this. Okay. I'll just skip the factoring part because I've done the calculation over there. If you factor this using factor by grouping, you're going to get x minus 3 times negative 3x plus 5. Therefore, if you ask when is this equal to 0, it's going to be 0 at x equals to 5 over 3 and 3. These are the places when y prime is equal to 0. These are critical numbers. Critical numbers. Now, why do we want the critical numbers? Because in order to sketch it, we need the signs of y prime. We need to know when it's increasing or decreasing. And in order to figure out when the y prime is positive or negative, you first draw the number line, place the values where y prime is equal to 0, and then you choose test values before and after. 5/3 is like 1.66, so between 1.66 and 3, you have the wonderful value 2 as a test point. 4 is the next value after 3. Before this, I can use 1 as the test point. And what you have to do is you have to plug in 1 in here, 2 in here, and one by one. Okay, so if I plug in 1, it's negative 3 plus 14 minus 15. It's negative 4, so you get a minus value here, negative 4. If I plug in 2, 2 squared is 4, 4 times negative 3 is positive 12, plus 28, so that's positive 14. No. 2 times, that's 28 minus 12. Positive 16, and 16 minus 15 is 1. So if you plug in 2, you get positive 1, which is plus. And then if you plug in 4, that's negative 48, plus 52. So plus 4 minus 15, so that's negative 11, so you're going to get a minus value. Okay? So you have to plug in these values to this function to figure out its sign and determine whether this y prime is negative in which intervals and positive in which intervals. Okay? Just by sampling, you can figure out that y prime is negative in this entire interval until you reach 5 over 3. Okay. Now, what does that mean for y? It means that the graph is decreasing, decreasing, and decreasing. Therefore, at 5 over 3, what kind of extrema do you have? Relative?
Minimum.
Relative minimum. How about this point? Relative maximum. At 3, you have relative maximum. Now, since relative minimum and relative maximums are actual points on the graph, it would be nice if you can plug this into the original function and figure out the coordinates. Now, I did this calculation in a separate place because it's kind of not so interesting. You just have to plug in these numbers and calculate this. It's a lot of annoying fractions. So if you plug in 5 over 3 to this function, you're going to get this. If you plug in 3, well, that one I didn't do, so 9 times 7 is 63 minus 27, 36, minus 36 minus 4, negative 9. Okay, so negative 9. Oh, yeah. So you're going to get 3 comma negative 9. Okay. And this is the relative minimum. And this is relative max. Now for the inflection point, we need the second derivative. Second derivative, if I differentiate this, I get negative 6x plus 14. So negative 6x plus 14 set to 0 gives you x equals to 14 over 6, which is 7 over 3. So 7 over 3 is probably an inflection point. It doesn't guarantee, I mean, being 0 of the y double prime doesn't guarantee being an inflection point. It must have a sign change before and after, but because this is a linear function, it's probably going to change its sign afterwards, okay? Yeah, so you can just plug in 4 as a test point and easily get negative here, 24, so that's negative 10. I can plug in 0 as a test point here. If I plug in 0, you get positive 14, so that's plus. So we do know that y double prime, since it's plus before 7 over 3 and after 7 over 3 it's negative, there is a change in concavity, therefore 7 over 3 does give you an inflection point. Okay. The inflection point, did anyone calculate the y value of the inflection point? I was hoping I didn't have to do this. Let's see. 7 over 3. 7 cubed, 3 cubed, minus plus 3 squared 7 cubed. I don't like fractions. I don't like decimals. I want fractions. Times 3 times 3, 2, 343 times 2, 686 over 27 with a minus. No, it will be a plus. Okay. And then minus 105 over 3 times 9, 945, 27. So you're going to get 945 minus 686. What's that? 935 259. Okay, so it'll be negative 259 over 27. Sorry about that. I should have worked that out too. So that's your inflection point. Now putting all these together, we can draw the graph. Let's try this. So at 5 over 3, you're going to have a relative max. At 7 over 3, you're going to get an inflection point. At 3, you're going to get relative min and relative max. This will be the inflection. The graph will be passing through the origin. It's going to come down. And actually, it's going to be very steep. It has to go, see, negative 275 over 27. 27 over 27 is about 10, right? 270 divided by 27 is about 10. So this is slightly more than negative, lower than negative 10. So it goes pretty far down. So it goes very far down. And then it goes up. And there's a change in concavity at 7 over 3. And it should do this. And then the coordinates are as written over there. 5 over 3, comma, negative 275 over 27 is the relative minimum. The inflection point here is 7 over 3, comma, negative 259 over 27. And the maximum point is 3, comma, negative 9. So that's the answer. When you sketch your graph, you should make sure you're writing all the coordinates of the x and y intercepts, and also the coordinates of the relative max, relative min, inflection point. And if it does have any asymptote, you should also figure that out too. Now this one, I know that it doesn't have an asymptote because it's a polynomial. Actually, if you recall what you learned in pre-calculus, you also learned the end behavior. If it's negative x to an odd power, the end behavior goes like this way and that way. Okay? So that also helps.